Chapter 2, Section 1, Problem 1D. Determine if the following sets and operations form a group. So here our set is going to be the set of all rational numbers not equal to -1, and our operation star is going to be a star b equals a plus b plus ab. To check if something's a group, we need the definition of a group. It's a set and an operation with these 4 conditions that we'll check one by one. We also need to remember that a rational number is a ratio of 2 integers, and most importantly, don't forget that the denominator cannot equal 0. And we're going to use the fact that sums and products of rational numbers are always rational numbers. So let's check our first condition, whether G is closed. The closed condition means that if any 2 members of the group are picked and we apply the operation star to them, we get another member of the group. Well, we just said that the sum and product of rational numbers always are rational numbers. So we know that a plus b plus ab is going to be a rational number, but we still have to check if that rational number is -1. Remember, -1 is not part of our set. So let's check that. A plus b plus ab equals -1. In order for that to happen, we see one way is that a equals -1. Well, we could have just as easily solved this, rearranged this for b, and seen that b equals -1 is also a solution here. And in fact, a or b equaling -1 is the only way to solve this equation. So as long as a or b is not -1, then the result of star will not be -1, which is exactly what we wanted. Remember, we took 2 members of the group, which are rational numbers not equal to -1, and we applied our operation, and we got something that was a rational number not equal to -1, therefore the closed condition is held. Number 2, G is associative. Again, we need to show these 2 equations are equal, and the only difference is in our first equation we apply b star c first, and in the second equation we apply a star b first. Rearranging, doing some arithmetic, we say that they're equal. Number 3, looking for an identity element. We often check E equals 0 for anything with addition, and E equals 1 for anything with multiplication. Here we just guess E equals 0. It's a good guess. A star E equals A, so A star 0 is going to equal A, and then we see the same thing in addition for E star A, still equals A. So this is our identity element. We also need to make sure that this is the unique identity element. Here we claim that it is, but if there was another such E that worked, that was a member of G, then this condition would have failed. Condition 4, the inverse condition, we're going to be looking at the equation A star B equals E, and remember that E equals 0. E is the unique identity element for this potential group. So looking at this equation, we assume that A is a member of the group. So think of that as an input, and we're solving for B, and we want to show that B is a member of the group. So when we solve for B in our equation, A star B equals 0, we get B equals -A divided by 1 plus A. The question is this a member of the set? In order to be a member of the set, you have to not be equal to -1. We see that the numerator and the denominator can never be equal, so this B can never be -1. Is B rational? Well, it looks rational, right? We can assume that A is a member of the set. So A is a rational number not equal to -1, and we know from our claim that adding, multiplying, dividing, etc. rational numbers always yields a rational number, but we do need to be worried about whether the denominator can equal 0. 1 plus A, though, cannot equal 0 because A is a member of the set, and the set does not include -1, so A can never be equal to -1. Therefore, B is a member of the set, and our condition 4, the inverse condition, holds, which is the last condition to be a group, so we conclude that G and this operation star indeed do form a group.